So we're finally here at the last section, and this is a specific method of creating power series for a given function. This is section 11.10 and technically 11.11 as well. And this is on the Taylor and Maclaurin series. Let's suppose we have a function, f of x, which is equal to a Taylor series. Or, it's not a Taylor series yet. Well, suppose we have a function f of x which is equal to a power series. N equals 0 to infinity c sub n times x minus a to the n. And this has a center of a. The radius of convergence is going to be as yet unknown, but we'll say it's for some radius of convergence, x minus a less than r. Well, since these two things are equal, technically as functions, then they must have the same derivative. And specifically, if they're equal, then when I plug in a for x, I should get the same number on both sides. So I'm saying that f of x is equal to c sub n, not c sub n, c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared plus, we'll go up to c sub 3 times x minus a cubed forever. Well, what must be true is if I plug in a, both sides of this equation would have to be equal. Specifically, since a is the center of this series. So I'll get c sub 0 plus, but when I plug in a, all of these terms become 0. So that finds us the first coefficient. If these two things are equal, then their derivatives must be equal. So f prime of x, which is equal to 0 plus c sub 1 plus 2c sub 2 times x minus a plus 3c sub 3 times x minus a squared, etc. If I plug in a again, I'm going to get c sub 1 plus, and again, all of these terms go to 0. If I take the second derivative, I'm going to get 0 plus 2c sub 2 plus 3 times 2, so 6 c sub 3 times x minus a plus, what would I have for the fourth term? I would have 4 times 3 times c sub 4 times x minus a squared, and that would proceed on forever. And when I plug in a again, well, I get 2c sub 2 plus all the terms left over still have x minus a, so they go to 0. Which means my c sub 2 is equal to f prime of a divided by 2. And if I proceed with this pattern, I'm going to find out in general, after I take all the derivatives, I'm going to develop a pattern, and that pattern is going to be f prime, or not f prime, but the nth derivative, fn of a, will end up being equal to n factorial times c sub n, which means my c sub n will be equal to f nth derivative evaluated at a divided by n factorial, which tells me that my original function has the power series n equals to 0 to infinity. My c sub n is f nth derivative evaluated at a divided by n factorial multiplied by x minus a to the n. And this construction, power series with this coefficient term, is called a Taylor series. In the special case that the center is 0, we call it a Maclaurin series. But since the Maclaurin series is just a Taylor series, I'm just going to call everything a Taylor series. And that would look like f of x equal to the sum from n equals 0 to infinity f n of 0 over n factorial times x minus a, nope, just x to the n. And what this does is, well, this provides a really handy way for us to evaluate or find a power series for any given function. So if I wanted to find a Taylor series for, say, e to the x, well, every Taylor series is going to have exactly the same formula for its construction. It's going to be the sum from n equals 0 to infinity. I'm going to take a bunch of derivatives. I should center it somewhere. So I'll say I'm going to center it at 0. Divided by n factorial multiplied by x to the n. So what I have to do for these problems is essentially find out all the derivatives and evaluate them at the center of my series. So it might be handy to draw a chart, but in general we're going to want to take a bunch of derivatives until we see some kind of a pattern developing so that I can write out my constant for the series in a nice way. So if I take the first, second, third, and fourth derivatives, well, the derivative of e to the x is just e to the x, which is quite convenient. So these are all 1. Which means my fn of 0 is always equal to 1. Which means that e to the x is equal to the power series n equals 0 to infinity 1 over n factorial times x to the n. And I think we may have tested the radius of convergence for a series like this before, but this is actually going to be have a radius of convergence which is infinite. But I can do all sorts of things with these because this is a function which is now equal to the Taylor series, or equal to a power series. So if I wanted to find, for example, find e to the 4x minus 3 as a power series, well, all I would have to do actually is plug it into the power series I already have from up there, because I know that f of x equal to e to the x is equal to sum n equals 0 to infinity 1 over n factorial x to the n, which means that f of 4x minus 3, which is equal to e to the 4x minus 3, must be equal to the sum from n equals 0 to infinity of, let's see, I'll have 4x minus 3 to the n, still divided by n factorial. And one of the great things about the power series for e, or e to the x, is its radius convergence is always going to end up being infinite. But why do we want to do this? Why do we care so much about having an easy to construct power series for all these functions? Is, well, the Taylor polynomial. So if I take the partial sum of a power series in general, I'm going to get a polynomial, because the power series really is just an infinitely long polynomial. But in particular, if I take the partial sum of a Taylor series, I'll have what's called the Taylor polynomial, and it's going to serve as an approximation of my function. Because if I asked you to find out what e squared is equal to, you would be kind of stuck. There's no way for us to do that really by hand except for with a calculator. However, a Taylor series or polynomial is much easier to evaluate. So here I'm using the notation t sub 5. And t sub 5 would be the 5th degree Taylor polynomial. or it would be the sum from n equals 0 up to 5 of the Taylor series. So I've been using e to the x. Let me add an x on here. So this would be x to the n divided by n factorial. So actually, let me write this one out. This is equal to 1 for the n equals 0 term, because 0 factorial is defined to be 1, plus the n equals 1 term, which is x over 1, plus x squared over 2, plus x cubed over 3 factorial, x to the 4th over 4 factorial, plus x to the 5th over 5 factorial. Now if I write those out, expanding the factorials, I'd have 1 plus x squared over 2, plus x cubed over 6, plus x to the 4th over 24, plus x to the 5th over 120. So if I wanted to estimate e squared, all I would have to do is plug in 2 to this polynomial, and I can definitely do that by hand. It might take a while, but I can do it by hand. So what I would be writing is that e squared is approximately t sub 5 of 2, which is 1 plus 2, plus 4 divided by 2, plus 8 divided by 6, plus 32 divided by 24. No, I did that wrong. 2 to the 4th is 16. This one, though, 2 to the 5th is 32 divided by 120. And, while I'm here, I might as well go ahead and try to work these fractions. So this much is 5. This is 4 over 3 plus, I can factor out an 8 from the top and the bottom, so this is 2 over 3. Great. 120 though, this one's harder. I'll have 16 over 60, or 8 over 30, or 4 over 15, and I think I'm stuck there, plus 4 over 15. 4 thirds plus 2 thirds, that's equal to a total of 2. So this is equal to 7 plus 4 over 15. So I need 7 times 15, which if I'm not mistaken is 105 over 15 plus 4 over 15, or 109 over 15. So one of these two representations is my estimation for e squared. But since this is an estimation, the real big question is, how bad is this estimation? Or, if you're an optimist, how good is this estimation? For that, we have the Taylor inequality. Or I'll sometimes call it the Taylor series remainder, because that's what it is. They're kind of interchangeable terms. But there's a lot of letters in the Taylor inequality, so we'll have to be careful about what we're looking at. So if f of x is equal to a Taylor series, I'll name that with a t, which is equal to the nth degree Taylor polynomial plus the remainder of using the nth degree polynomial, and x is in the interval of convergence, specifically that's like saying x minus a, which is the center, is less than r, which is the radius of convergence. I said this slightly backwards, but the function is only equal to its power series on the interval of convergence, and otherwise it doesn't make any sense. Then, for all x such that x minus a is less than or equal to some number d. So what I'm looking at is I'm looking at some interval, which is a subinterval of the interval of convergence. Specifically, if my interval of convergence is from here to here, specifically, if my interval of convergence is like so, then I'm going to be looking somewhere on the inside. Or, I mean, this d, you might as well just let it be the whole interval of convergence. If f n plus 1 of x is less than or equal to m for all x, oh, no, I already said that. For all x in there, if fn plus 1 of x is less than or equal to m, which basically says my next derivative, my n plus first derivative, has a bound. I find the maximum positive or negative value for my n plus first derivative for my function, and I plug it in like this. The remainder is less than or equal to this number m divided by n plus 1 factorial multiplied by x minus a to the n plus 1, which is basically looking at the next term of the Taylor series. So the Taylor series remainder is actually very close to the alternating series remainder. But what we're saying is that if I use the maximum value, positive or negative, of my next derivative after the point where I stopped and plug it into my Taylor series term, that's going to be my bound for the error. So let's try to make sense of this with the example I already have. We found that t sub 5 of 2 was equal to 7 plus 4 over 15, or 109 over 15, as an estimate for e squared. Here I used n equal to 5. So my question here is, how big is the error of this estimation? So since the Taylor series of e to the x I made was centered at 0, I'm going to use d equal to 3 in my Taylor series remainder, or Taylor inequality, because the radius of convergence of e to the x is infinite. And so if I try to find the n plus first derivative of e to the x, that's just going to be e to the x again, but it doesn't have a maximum value on the interval of convergence because the interval of convergence is all real numbers. And so that doesn't have a maximum value because it goes off towards infinity. So what I'm going to be doing, since my Taylor series is centered at 0, I'm going to cut it off here at d equal to 3. And right here was the number I was trying to estimate. X was equal to 2. Then, we need to find the m such that m is greater than the absolute value of f n plus 1, 5 plus 1 of x on the interval -3 to 3, which is this right here. That's when d is equal to 3. Well, the fifth, actually sixth, derivative of e to the x is e to the x. And the maximum value of e to the x on, these should be closed, negative 3 to 3 is actually going to be e cubed, because e to the x is strictly positive function. So e cubed is the maximum value. But I don't know what that value is off the top of my head. So what I'm going to use instead is e is less than 3, so I'm just going to use 27. 27 is greater than e cubed, which is greater than or equal to f to the 6th of x for every x on the interval. If I wanted a more specific remainder, I would use d equal to 2, but that's getting it very close to where I'm looking. Then the maximum error for my Taylor series will be less than or equal to my m, which is 27, divided by 5 plus 1 factorial times x minus a, which is 0, to the 5 plus 1, which is equal to 27 over 6 factorial times x to the 6th. But since my x is equal to 2 here, the remainder for evaluating 2 would be less than or equal to 27 over 6 factorial times 2 to the 6th, which is equal to, let me see here, I've got 3 times 3 times 3 times 2 times 2 times 2 times 2 times 2 times 2 divided by 6 factorial. There's 6, which is 3 times 2, times 5, times 4, which is 2 times 2, times 3, times 2, times 1. And I can cancel off a bunch of these numbers. One more. A 3, and a 3, and a 3, and a 3, which is equal to 8 over 5. That's actually not too great. Because I could be over 1 away from just using a fifth degree polynomial. If I had chosen d equal to 2, then instead of using 27, I would have used the number 9. But this would have, silly. What this would have done is it would have decreased my maximum possible error estimate by a factor of 3, giving me only 4/5, which is less than 1, which is a lot better actually. We'll notice, based on the formula for the error, the farther away I go from my center, the larger my error. And potentially, the derivative may cause my error to be larger as well. But also, the smaller I use, the smaller partial sum I take, the larger the error. If I take a very large partial sum, then this n plus 1 factorial will force me to have a very small error. So let's have another construction. Let's find the Taylor series for natural log of x, and we'll center it at x equal to 1. And the reason I chose x equal to 1 is because the function and its derivatives are going to be easy to calculate at x equal to 1. I could center it further out, like at x equal to 5 or something, but I don't know what natural log of 5 is. I could center it at e because I know what the natural log of e is, but the derivative of natural log of x is 1 over x, and I don't know what 1 over e is. So these are always the same formula, n equals 0 to infinity f n. I'm centering it at x equal to 1, so I'm going to plug in a 1 here, and factorial, and I'll have an x minus 1 to the n. So if I take the first, second, third, fourth, and let's say fifth derivatives, first derivative of natural log is 1 over x. The derivative of that is negative 1 over x squared. Derivative of that is positive 2 over x cubed, and then 2 times 3 over x to the fourth, this time negative. And then finally, I'll have a positive 2 times 3 times 4 over x to the fifth. So let's see if I can find a pattern for the derivatives. It looks like I'm alternating in signs because I have to multiply by a negative power exponent every time I use the product rule, or power rule. So I'll have negative 1. It looks like I'll be using n plus 1 because my first one is a 1, my second is negative, my third is positive, etc. And I'm going to be using, looks like, n minus 1 factorial divided by x to the n. If I were to evaluate this function at at 1, I'm going to have negative 1 to the n plus 1 times n minus 1 factorial divided by 1. Or I could rewrite this as negative 1 to the n minus 1 times n minus 1 factorial. So let's see if this fits over here. 1 factorial is 1. Negative 1 to the n minus 1 is 1. And sure enough, if I plug 1 into 1 over x, I get 1. For 2, if I plug in 1, I should get negative 1. Comparing with this function, if I have negative 1 to the 2 minus 1, I get a negative 1, okay, times n minus 1 factorial, that's 2 minus 1 factorial, which is 1 factorial, which is 1. So I get a negative 1 for plugging in here and for doing the function. And similarly, if I plug in 1 for the third derivative, I should get 2. Down here, if I plug in 3, I get negative 1 squared, that's positive, times 3 minus 1 factorial, which is just 2. And of course, if I move on to 4, I'm going to have negative 1 cubed, which is negative, times 4 minus 1 factorial, which is 3 times 2. So it seems this here is my coefficient. which means the natural log of x should be equal to the sum from n equals not 0, because the n equal to 0 term was a 0. So I'll go ahead and start this at 1 up to infinity. My coefficient was negative 1 to the n minus 1 times n minus 1 factorial divided by n factorial multiplied by x minus 1 to the n. But this simplifies because I've got a bunch of factorials there. To become negative 1 to the n minus 1 divided by n times x minus 1 to the n. So on this, if I do the root or the ratio test, I'm going to find that the radius of convergence is actually only 1. Which makes sense because at the center of this power series is at 1, but the natural log of 0 is undefined. It goes down to negative infinity. So let's go ahead and test this. I'll have the limit as n goes to infinity, absolute value, so I get to ignore the negative 1 to the n minus 1 part. I'll have x minus 1 to the n plus 1 over n plus 1 all over x minus 1 to the n over n. And if I simplify the fraction, I'll have x minus 1 to the n plus 1 divided by x minus 1 to the n multiplied by n over n plus 1. These cancel. Those don't cancel. Giving me the limit as n goes to infinity of absolute value of x minus 1 times n over n plus 1, which implies that x minus 1 should be less than 1. So there's my radius of convergence. To find my interval of convergence, I would test the endpoints. So if I plug in 0 for x, or if I plug in 2 for x, I'll have two different series. So n equals 1 to infinity, negative 1 to the n minus 1 times negative 1 to the n over n. And on the other hand, I'll go from n equals 0 to infinity. I'll have negative 1 to the n minus 1 multiplied by 1 to the n, which is just 1, so you'll ignore it, divided by n. Again, this is supposed to be from 1. But this series on the right is an alternating harmonic series. This converges. But this sum on the left, let's see, this is negative 1 to the 2n minus 1 divided by n. But 2n minus 1 is always odd, which means that every term of this series is actually negative, because negative 1 to an odd power is always going to be negative 1, and if it's always odd, then it's always negative. But that means that this is a harmonic series, and not alternating, so it must diverge. So this is a series which converges from 0 up to 2, including 2. Now supposing I wanted to find out what it converged to at 2, well, now notice something really interesting happens. The natural log of x is supposed to be equal to this series, n equals 0, not 0, every time. 1 to infinity, negative 1 to the n minus 1 over n times x minus 1 to the n, which means the natural log of 2 is equal to the sum from n equals 1 to infinity, negative 1 to the n minus 1 over n, times 1 to the n, which is just 1. But this means that natural log of 2 is equal to n equals 1 to infinity, negative 1 to the n minus 1 over n, which is exactly the alternating harmonic series. So what I recommend is grab a calculator and see just how many digits you have to include in order to get within 2 decimal digits of the natural log of 2. You're going to have a very, very long Taylor polynomial for this problem. For some common functions, we have some common Taylor polynomials. And a lot of them line up with what we did in the previous sections. If I have 1 over 1 minus x, then my Taylor polynomial will actually just be x to the n. Here's the x we've dealt with. This is a sum from n equals 0 to infinity of x to the n over n factorial. The natural log of x plus 1, which is a left shift, so instead of having a center of 1 like I just did before, I'll have a center of 0. This is equal to sum from n equals 0 to infinity, not 0, but 1, of negative 1 to the n minus 1, x to the n divided by n. I encourage you to find the Taylor series for sine of x, centered at 0, which would be very similar to if you tried to center it at another easy spot, which looks like pi over 2 or pi or 3 pi over 2, stuff like that. Pi over 4 is also an entertaining place to center it. The power series for sine actually skips a bunch of entries. So I should note here that for this Taylor series, the index n does not equal the degree of the polynomial. In fact, if I wanted t sub 3 for sine of x, I would only use the sum from n equals 0 up to 1, negative 1 to n, x to the 2n plus 1, all over 2n plus 1, factorial. So be sure to keep this in mind for sine and actually for cosine. Looks like tangent as well, because these use, these are the sine is an odd function, and so it's only going to be using odd power terms in the Taylor series. The cosine is an even function, so it will only be using even power terms. Tangent is also an odd function, so it will only use odd power terms. But the index of the series does not match up with the degree of the polynomial for the Taylor polynomial. If I wanted the 5th degree Taylor polynomial, for example, I would only use the sum from n equals 0 up to 2 for sine or for tangent. So be very careful with some of these Taylor series, because the remainder, when you're dealing with the Taylor polynomials and the error estimation with the remainder, those n's are for the degree of the polynomial. The remainder deals with the degree of the polynomial, which may or may not match with the index of your power series. So cosine of x, like sine of x, skips a bunch of terms. I go from x to the 2n over 2n quantity factorial. Tangent would be sine divided by cosine, but you can imagine that would really, really suck to do. It's bad enough to divide polynomials, but dividing infinitely long polynomials will pass. You could do it though, and you would probably end up with something that looks like this. And finally, I'll say that if you have any polynomial at all, then what's going to happen is if you try to find a Taylor series for a polynomial, you're just going to get the polynomial back. You're going to have a weird way of writing it, but once you did all the simplifying and stuff, a polynomial will look exactly like its Taylor series, because the Taylor series is just an infinitely long polynomial. And so if you already have a polynomial, then all of the higher degree terms are already going to be equal to 0.